Welcome to this lesson on using R to compute antiderivatives and evaluate definite integrals. So let's start with creating a function, and this should be a familiar command to you by now. We're going to have f just be the function x squared. So if I want to find the antiderivative of f, I simply use the command anti-d with a capital D, and then I need to indicate what the function is, f of x, and what the variable is. And this command is actually specially built for this class. It will help you find antiderivatives of even functions that don't have very simple antiderivatives. It does this numerically. So we'll compute antiderivative, and then we're simply going to plot the original function f, which if the function is y equals x squared, that should be a parabola. So let's just check that out and see that we get a parabola here. And if we plot the function capital F, and it's pretty standard to use capital F for an antiderivative, and we just add that to the same plot. So we are using the command here, add equals true. Then we see right here we get that function. And if you look a little bit, that looks a little bit like a cubic function. And we do know that if we compute the antiderivative of x squared using the power rule, we should get x cubed over 3. So computing antiderivatives and plotting them is a very simple thing. So let's see how we would use this to solve some of the problems that we did in the lectures. So let's look at the function g of t equals 2 to the t. In the example in one of the lectures on the bacteria colony, we had a rate of bacteria growth of 2 to the t. So we'll just let g be the function g of t equals 2 to the power t. And what you were asked to do in that problem was compute the integral from t equals 0 to 2 and find what the total change in bacteria was. So the way to do that is to compute the antiderivative for computing a definite integral. So we compute the antiderivative of g, and then we just use the fundamental theorem to say what's g of 2 minus g of 0. And if you go back to that lecture, I had told you that I had computed it and it was about 4.32. So this process is pretty straightforward. If you're trying to compute an integral of g, little g, from 0 to 2, you first find the antiderivative like we do when we compute things by hand, and then you plug in 2, plug in 0, and subtract. So let's do one more example. If we have two functions, h1 and h2, there is an example where we talked a little bit about area under a curve, and I indicated that we would talk more about that later. So let's just plot these guys first. So if we plot h1, we get something that looks like an upside down parabola there. And if we plot h2, we get this curve here. And so the question on the lecture module was, what's the area between these curves? And the rule basically said, well, you think of area under a curve as a definite integral. So you can think of area between curves as an integral from where the curves intersect to where they intersect again, the top function minus the bottom function. So there are a couple things we need to think about first. We first need to make sure we know where these points are, where the functions intersect. And this point right here is pretty easy. That's simply x equals 0. This point here we need to do something with R to help us either estimate that or find that exactly. And R's got some nice built-in commands. One of the ways to see where two functions are equal is to subtract them and set them equal to 0 and solve. And so R can do that in the following way. So the command find zeros, FINDZEROS, allows you to take some kind of function, and in this case it's the h1, which is the top function, minus h2, which is the bottom function, and I'm telling R that the variable is x, and then I'm saying where I want you to look for zeros. And in this picture I want you to look for zeros, meaning the functions would have to be equal, between 2 and 4. So R quickly tells us that it looks like there's a 0 at 3.11, and if we actually look, that looks really close. That's probably that 0 right there. We could similarly find zeros for the same function. This is going to seem a little silly. We'll find the 0 down here at x equals 0. So we told R this time that look for some zeros when you subtract the two functions. So basically that's saying again where those two functions are equal. When x is between, and this is a little hard to see because it wrapped around, but negative 1 to 1. And so it said, oh, there's 1, 0. That's it. It's right there at x equals 0. Okay, so at least now we know the limits of the definite integral. So if we could integrate h1 minus h2 from 0 to 1, 0 to 3.11, we'd be in business. And R lets us do this just like we did the previous examples. We simply need to find some antiderivatives. So the rule says find the antiderivative of little h1, and we'll just call that capital H1. Find the antiderivative of little h2. That's capital H2. And then we just need to evaluate both of those and subtract. So very simple to make a new function that just is the difference of the antiderivatives. So we'll just call that h. And then just say what's the h value, the antiderivative of both of those at 3.11 minus the antiderivative at 0. And we should get about 5.9. And it's always good to take a look at your graph and think about the area between the curves and see if 5.99 makes sense. Here are the tick marks here. So any box about that big is 1 unit. It seems reasonable that the area might be about 6 units. So basically it's pretty simple to compute definite integrals in R. You just define a function, find the antiderivative, and use the fundamental theorem to plug in the limits. So thanks for listening.